show my talent off. I go on stage and I show my talent and I make money.
This is where we left off before lunch. We have a problem is which before lunch we were talking about, okay, if you combine solutions together that have ions, if there is an insoluble or a not very soluble substance that might be made from the ions, you're going to figure out which one most likely would form. And if the Q value, after you mix these ions together, is greater than K for a reaction, it will shift back the other way and you'll see a solid form. That would be that precipitate. Okay, so here's number 56 in the book. It's not exactly what we're doing, but you have to use the concept. You're given the KSP of aluminum hydroxide. At what pH will a 0.2 molar aluminum solution begin to show precipitation? Just going to turn the lights on this week. So this is what I was talking about when I said when you write the chemical equation, always write the solid on the left and then it breaking up into the ions. Even though in this case, you're starting with this. You're starting with aluminum ions and hydroxide ions and the reaction has to go back that way. The reason that we write the equation like this is because we're given the KSP. KSP implies that you have the solid changing to the ions. That's the way that KSP is always written. Now you might say, well, could we turn the reaction around and just take the inverse of KSP? Yeah. I don't recommend it. You could do it. And the reason I don't recommend it is because I'm just one that tried to do things systematically. I like to try to come up with, okay, we'll just do the same thing every time so we don't get tripped up. But you could certainly do something like that. All right. We're given 0.2 molar aluminum solution. And we start adding hydroxide very, very slowly until we start to see a precipitate form. At what pH? In other words, what is the concentration of hydroxide that it would take to get a precipitate of aluminum hydroxide? So this is the unknown. Now, if a precipitate is going to be made, that means that the reaction has to shift that way, right? We start with none of the reactant. There is none of this. We're only starting with that stuff on the right. So we've got to have the reaction shift this way. And the only way a reaction can shift to the left is what? What about Q? This is the only way a reaction will shift to the left if Q is greater than K. So this has to be true. Now we're not at equilibrium, so we're not going to say that K equals 0.2 times that number. It's not at equilibrium. So it is true, though, because it's not at equilibrium, Q is the concentration of Al times the concentration of OH cubed. Q is equal to that because the reaction is not yet at equilibrium. We know this term. We don't know this term. Now here's another hang-up that people run into. People want to think that for the hydroxide you need to plug in a 3x for the hydroxide. That's not true either. Externally you're adding hydroxide to it. So as soon as you add some hydroxide, you're going to have some finite molarity of hydroxide in there. Or if you add a little bit more hydroxide, then the concentration changes, but it's some value. I do know that they react in a 1:3 ratio. But we're going to take care of that because it's raised to the third power. You don't have to multiply that amount by 3. That would change what the concentration is. The concentration is what it is, so don't multiply it by 3. So, if we know that in order to make a precipitate, the Q has to be greater than K, and we know what the expression for Q is, that means that this thing right here has to be greater than K. So, it's going to look like this. Al is 0.2 times the hydroxide concentration has got to be greater than, I'll just write, that's not 1, 2, times 10 to the negative 32nd. Now can you solve for the hydroxide concentration and find the pH? That's what we have to do. Just take that number, divide by 0.2, and take the cube root. And so mathematically, that's not very hard. 2 divided by 0.2 is 10. So that makes that 1 times 10 to the negative 31st. I don't know what the cube root of that is. Anybody have it? What is it?
Oh, 4.64.
The negative. Negative 11. Yeah, okay. Okay, that polarity. So then you'll, excuse me, find the pH. Now, I transformed this greater than sign into an equal sign. That really was not on purpose. It should still be greater than. The hydroxide, this would be the what? This would be the concentration of hydroxide that would just be at the brink of shifting this way. If we have a concentration of hydroxide exactly this, then no precipitate is going to form because the reaction's at equilibrium. But as soon as it goes higher than this, then Q is going to be greater than K. And send it that way. So I do have to say like that. And so that's a pH of like 3.7, I think. Does that seem right? 3.7. Yeah. The pH then has to be greater than 3.7. Now we'll use this idea in the next example too. The next example though goes another step. Anybody have any questions about that?
Wait, so,
Go ahead.
like if this, like, let's say if this question you say, we always have to have the like greater than sign, or like less than sign.
For something like this, when we're talking about beginning to show precipitation, just tell me what the hydroxide concentration has to be. If I decide what range of concentrations or whatever, you'd have to say greater. But you'll see, when you start doing some of the problems, you'll see that most of the time it'll just be at this concentration. That's when the precipitation would start. So you know that anything above that is going to precipitate anyway. Okay. All right. Now, not only will we need to determine if a precipitate will occur, but also we need to determine what the final concentrations of ions will be. What concentrations will there be at the end? Now, this is going to be a technique that we've used already once this year in the equilibrium. I think it was in chapter 14, the acid base, where we're going to have to take a reaction all the way to completion and then have it drift back to equilibrium. And hopefully that comes back to you some when we do it. But go ahead, I'll give you a second if you want to write that down. We have a modified ice table, just slightly modified. David?
The statistics are
Yes, 28 minutes. Yep. So good thing you didn't have chemistry 5th or 6th hour. You would have been like ripped off.
So what will you do for to your 600 hour?
I have Chem 1 5th hour, so we'll be able to squash it down. It's fine. And Chem 1, we just burn stuff and laugh all the time. It's a little bit different with this class. Then you come to this class and there's weeping and gnashing of teeth. So okay, can we go on? One more example and then we're done. So it's 11:49, we're doing great. So I know this is a kind of a novel kind of a question. So we have a solution prepared when we mix 75 ml of barium with 125 ml of sulfate. So these two ions could possibly make a precipitate. Well, the question is, what are the concentrations of the barium and sulfate ions in the solution, possibly after they've made a precipitate? And spoiler alert, they'll probably make a precipitate. Yeah, you have to know the solubility rules to know which one is the most likely precipitate.
ACL soluble. ACL soluble.
A is so it's BaSO4.
Yep.
BaSO4 is not.
Yeah. The big thing about the solubility rule, just remember in general what things are always soluble, and that usually will get you out of trouble. Potassium ions are always soluble, so potassium with the other thing is not going to be the precipitate, so you have to take the other combination. I do want you to note this thing right here. There is a solubility table, KSP table, right after the KB table in the appendix of the book.
Yeah.
Thank you, David. I talked about the chemical equation. What do we write out? We have a solution with barium and a solution with sulfate. So we're going to put those together into the same container. You have barium and sulfate ions, and you expect them to make barium sulfate. But like I told you, you want to always write the chemical equation with the solid on the left. So the reaction, if it happens, is going to have to go from right to left. So we're going to write it like this. The possible precipitate is going to be this. And the products would be barium and sulfate, aqueous. Okay, so we start with this. Of course, the K is given to you. K is right there for this dissociation reaction. What are the initial concentrations of barium and sulfate? Now, you're tempted to say, oh, the initial concentration of barium is 0.02. No, because two solutions got mixed together. Therefore, we have to use the dilution formula and figure out what the initial concentrations are after they're diluted, mixed with the other solution. So, for the barium ion concentration, this is M1V1 equals M2V2. You'd have to take 0.02 times 75 and then divide it by 200, which is the total volume. What is it?
3 over 400. So
0.0075. Very good, Siddharth. Thanks. What about the sulfate? Same thing with the sulfate. It gets diluted. 125 times 0.04 divided by 200.